Welcome back to ECE 220. Several announcements, and maybe the ordering is messing you up, but I wanted to make you aware of when you didn't have to attend class. That's why those were listed first, but in fact they actually date-wise go near the bottom, if that makes any sense. But we won't be here a week from today. The day before Thanksgiving, we won't be in the classroom. And the following week, I guess a week after Thanksgiving, is exam number 4. So exam number 4 is on the 5th of December, and then the following day, the 6th of December, we won't have class, and we will not have class the Wednesday corresponding to the last day of class. Group A, you are having your lab number 5, which is the final lab, this week. You will then submit that on the Wednesday that we're not attending class. But Group B, your lab number 4 report is due today, and your Group B's lab number 5 pre-lab is due Saturday. And then you will have a lab on Tuesday. That will be the last lab for the semester for all groups on Tuesday of next week. Today what I want to do is summarize how we can express these passive elements in the frequency domain when we're now in sinusoidal steady state. We can now describe those by complex numbers. And the resistors come over unchanged. Inductors need to be treated as j omega L, and capacitors are 1 over j omega C. Obviously, you have to know what the frequency is if you want to compute the actual complex value of that impedance. And then we'll go through some examples. I want to maybe quickly go through this. So I'm sort of reading to you. This is kind of a movie you can watch, but this should be familiar to you. What we've already talked about, this is more of a summary. We have our time domain and our frequency domain, and we want to be able to work in both. In the time domain, we have Ohm's law, and in the frequency domain, we also have Ohm's law. And now we're looking at the resistor as our passive element. And if you wanted to redraw your circuit in the frequency domain, wherever you have resistors, that sketch would look the same. You would just label those now with current phasors and voltage phasors, observing the passive sign convention as we've been doing all along. We're going our current, the reference direction of our current is going into the positively labeled voltage symbol on that resistor. If we wanted to, we could put on our cap, our 2-year-old cap, and ask why. And here I'm trying to explain or give you some reasoning why we see the same relationship in the time domain and the frequency domain for a resistor. We have our, and this again, we're already in sinusoidal steady state. The transient has gone. Voltage is Ri, and if we let I on our resistor be I sub m cosine omega t plus theta, we now know that that's equivalent to the real component of this complex exponential. So that I is also the real in arguments. I am the magnitude of the current, e to the j omega t plus theta. We can split apart that complex exponential into a time-varying piece, e to the j omega t, and a time-invariant piece, e to the j theta. And I did that without really showing you the steps, but underneath I said with I sub m bar, the phasor of the current, has a magnitude I sub m, which is what the magnitude was in our time domain cosine waveform, and the phase shift we could either write as e to the j theta or at angle theta. Those are equivalent. We're just maybe reducing the symbols that we have to write down, or the characters, by just saying angle theta. But that really is equivalent to e to the j theta. The voltage is given by Ohm's law. We scale by R, the current. Again, we're taking the real part of what's associated with that complex exponential, and the resistor value, since it's constant, it can easily slide inside the curly braces. And now, if I separate out the rotating phasor from the time invariant piece, I can identify I sub m bar, the phasor of the current. But now I have some voltage phasor that is spinning at the same rate or frequency omega, and that's this R I sub m bar. That means then if we wanted to talk about the voltage phasor, and here I better bar that, V sub m bar is equal to R I sub m bar, or the impedance of our resistor is just the ratio of our voltage phasor and our current phasor, which is R. Which really just is another way, another way of thinking of that is if you're looking at just a purely resistive circuit, then all of your voltages and currents would be aligned in terms of the peaks would be aligned with the peaks and the valleys with the valleys. Now for a resistive element itself, that same thing holds true. If you look at the current on that resistor or through that resistor compared to its voltage, you're going to see that the voltage and current align. They obviously will have different magnitudes depending on the value of that proportionality constant R, which is your resistor. That gets a little bit more involved when you talk about the inductor, because now we have a differential relationship between our voltage and current. We know from Eli that V is equal to L di dt, and that's then we can show that that's in the frequency domain consistent with multiplying by j omega L. So if you now see an inductor in your circuit and you want to analyze this circuit in sinusoidal steady state, you can go through your circuit and change all of your inductors to have an impedance of j omega L. And you can go through the same thought process or derivation or discussion and hopefully see that in fact we have answered the why question for the inductor, and it's really just justifying that the impedance of an inductor is j omega L. What we can then answer is the following. For an inductor, we know that the voltage and current are not aligned. They're actually 90 degrees apart. Now these next two statements, which are equivalent, I'm wanting you to inform me which word goes in the blank, leading or lagging, or leads and lags, based on this current voltage relationship of our inductor in the frequency domain. Can you tell by looking at, and I need to be a little bit more careful with my bars, can you tell from that V is equal to j omega L times I sub m bar how to fill in these blanks? Voltage blanks current by 90 degrees. So maybe I'll query the game show audience. And now we have leading for 1 and lagging for 2. And I need you to show me your fingers when I say the first blue sentence, voltage blanks the current by 90 degrees. When I count to 3, I want you to say either 1 for leading or 2 for lagging. Ready? 1, 2, 3. So we have a little confusion, not too much, but here if you look at the right-hand side, that J, what's that J correspond to in terms of an angle? If you needed to now say, oh, where is J in the complex plane, what's the angle that gets you there? 90 degrees. So in fact, you have to add 90 to the currents phase to obtain the voltages phase. That is one way of saying, oh, the voltage is 90 degrees ahead of, in our picture, the current. So in fact, the voltage does lead the current in an inductor by 90 degrees. If you needed to draw that, you would say, oh, if this is now my current, where would you draw the voltage phasor? It would be at right angles, and if, depending on its magnitude, it's now relative to this counterclockwise positive direction of angle, there is now your voltage phasor on this inductor. Or you could say the current lags voltage by 90 degrees. Those are equivalent statements. And when you get to the next class, 320, and you're talking about power, leading and lagging will be used a lot. You'll be asking, oh, is this a leading power factor? Is it a lagging power factor? Etc. And so knowing those terms is important. And here's a picture that hopefully depicts that. Not a great picture, but you can maybe see that we have a blue curve and a red curve. And the blue curve is the voltage. That's actually ahead of, or the peaks occur a quarter of a period ahead of or before the red peaks. So I've tried to color code this. If you're printing it out on a black and white printer, it may not be very clear which is which, so you might want to label those or somehow indicate which one goes with what line or figure in that diagram. Our phase shift is 90 degrees, and what's a full cycle? A full cycle is 360, 4 of those 90s. So that's why you're staggered 1/4 of a period between the blue curve and the red curve for this inductor, because they do differ by 90 degrees. The capacitor is derived with a similar discussion. I'm not going to go through it, but now what you do need to realize is if you now are translating a time domain circuit into a frequency domain circuit, replace your capacitors with 1 over j omega c. That will be their impedance, where the omega is coming to us as the frequency that we are working at or examining in that sinusoidal steady state condition. And here's the why behind that. It proceeds in a similar manner. And now, if you're looking at the old notes, I forgot to change the label. It is capacitor that we're dealing with now. I think last night in my haste to get this published, maybe, I don't know if it exceeded 9 p or was below 9 or not, but I think it was, barely, before 9 p.m. But now that should be the capacitor as far as what we're asking for now. Now in terms of, and I've already given you the answer, haven't I? If you can relate the waveforms, the sinusoids, to this question. I've indicated that the voltage is red and the current is blue in this case, and that means that the voltage for a capacitor does what relative to the current? The voltage blanks the current by 90 degrees. Now it's a quarter of a period different, and in fact the red curve occurs later in time. That green axis is the time axis. The red curve is later, and that's actually corresponding to the voltage. So in fact the voltage does just the opposite for a capacitor as it does with a inductor. And you can see that with this current expression. You now say I sub m is equal to j omega c v sub m. Then I is 90 degrees ahead of the voltage phasor due to that relationship. Or you could then say that the current leads the voltage by 90 degrees. All of this now allows us to generalize and say, oh, when we have these phasor quantities of voltage and current, now they're related by an impedance Z. And that impedance could be made up of a collection of R's, L's, and C's. Which means now that we have our impedance Z as some complex number. It's not just a resistor necessarily. It's not just an inductor. It's a collection of those. And now, if depending on what we're measuring our voltage with respect to, Z is a complex number. And Z is our impedance, and it's not a phasor. Our currents and voltages are shaking. They're oscillating, and those are the barred quantities. And they had that e to the j omega t inside the real, or when we were expressing those as complex exponentials, we had to extract from this argument of the real expression the e to the j theta and the magnitude. And we basically kept the e to the j omega t on the side. The v and the I are phasors. And maybe to be consistent, I should just say v sub m. And we actually label or introduce some new terms. Now that we have this impedance Z as a complex number, we can break that into its rectangular form, and the real piece is just the resistance presented by that impedance. Now think of the impedance as a box, and it maybe has a resistive component and a inductive or capacitive component. And it's probably got both of those, but net, one, it may look more inductive than it does capacitive. And that's what we need to get comfortable with, and that imaginary component is called reactance. We have resistance plus J reactance. That's the rectangular form of Z. And R and X, those are real numbers. You combine them by saying, oh, X is in the vertical direction, and that's how we get our complex number Z, or the complex impedance. We say whatever our resistance is, that's in the real direction. Now our imaginary component is influenced by the inductive nature or capacitive nature of our circuit. And if we look at this impedance Z, we can determine what this box looks more like. Does it look more like an inductor, or does it look more like a capacitor in terms of its combination with the resistance? If our reactance is positive, remember we have j omega L, and that was in the numerator. That was the impedance of our inductor. That's a positive X. Our X is omega L. When we were looking at the impedance of a capacitor, Z sub C was 1 over j omega C. The j in the denominator actually looks like a negative j if we bring it upstairs and put it in the numerator. There is now our negative value of X. We now have minus 1 over omega C for the reactance of a capacitor. We can then infer what this circuit is. It behaving more inductively or capacitively? And now we can sort of start saying, oh, is something leading or lagging based on that property or characteristic of our impedance? Let's look at an example. Suppose now somebody combines a resistor, inductor, and a capacitor. A resistor, an inductor, and a capacitor walk into a ECE 220 class with various values, and in this particular case, the resistor is 2. What is buried in this example? If these three elements have walked into a restaurant, R, L, and C, what are we not seeing here? What is hidden from us in this description? Omega. How they are shaking. That's already been computed in the J3. That 3 is omega L. The minus 2 is the minus 1 over omega C. The omega has already been taken into account. What's the equivalent impedance across terminals A and B? And now you're just playing with complex numbers. You can say, oh, that is in fact a real part of 2 and an imaginary part of 1. Which means, effectively, you could redraw that original schematic with R, L, and C as just an R and an L, where the resistor is 2 and the inductor is J. Effectively now, your interconnection of R, L, and C effectively look like an RL interconnected set of passive elements. And now that we can talk about impedance in terms of or like complex numbers, we can start identifying or finding different pieces of this impedance. We could find the magnitude of the impedance. And if our impedance is now the resistance plus the, what was the X called? Was that the reactance? So now how do we describe the magnitude of Z in terms of R and X? That's just now a property of complex numbers. We can say, oh, that's now just the square root of our resistive part squared plus the imaginary part squared. The angle of that impedance, we just say, oh, that's the inverse tangent of the vertical piece over the real component. And what am I not saying here that you know I want to say? Pay attention to your quadrant, right? Where is X? Is it up or down? Is it inductive or capacitive? And that influences the angle of your impedance. If you had a positive angle, what do you know about that box that has R, L's, and C's in it? Is it inductive or is it capacitive? If your angle is positive, it's inductive. If that angle of your impedance is negative, then it's capacitive in nature. You can also then extract the real component and the reactive component by trigonometry. You can say, oh, if I now knew the magnitude and the angle, I can now rewrite or find the real component by just taking or just projecting that magnitude onto the real axis, or the resistive axis in this case. Likewise, you could find the reactive component, the reactance, by projecting onto the vertical axis. And that's displayed here graphically, where this particular piece is R and there's JX. Depending on what you're given, you can now find many different quantities of interest. What's the magnitude of your impedance? What's the angle of your impedance? What's the sign of that angle? That gives you important information. Let's now try out these skills. Well, now we're going to try to develop some skills. Let's now try to put to use what we've learned, our knowledge. And in analyzing this circuit, let's find the voltage. And here it's been in this configuration forever. That means the transient is gone, and I want to know what is V sub c of t as a waveform. What's the capacitor's voltage drop from left to right? Giving you a little time to sketch and think. How are we going to approach this problem? Any thoughts? Somebody got a little aggressive with all the sources, didn't they? They weren't in our lab. We don't have that many function generators at our bench, do we? Is there any, how could we approach this problem with so many sources? You could combine them. I was thinking you might suggest superposition, which you could, but in that case you would have to solve 3 different problems. Let's just combine those sources. Since they're in series, they better add up and just get one effective source. We have a cosine, we have a sine, and we have a cosine. Why is it that we can combine them? Why can we combine them, and why is superposition not maybe the best for this particular problem? They share the same frequency. If one of these cosines was a different frequency, maybe the sine was a different frequency, then we better say, wait a minute, my L's and C's are going to be different because those are at different frequencies. So you would redraw this for each of those new frequencied sources and say, let me just apply superposition. And then V sub C would be a combination of those multiple frequencies. In this case, we have the single frequency, 4 radians per second. We can combine all of those. We know how to combine sines and cosines. We can do our graphical tool if we want to. Or we can now put them into phasor form and combine the phasors and then we have just one source. If we now combine the sources, how do we want to combine them? Oh, and these are even directed in opposite ways, aren't they? The plus signs are not all in the same orientation as we go around that mesh or that loop. The 7 is, if I now said, oh, I'm really kind of interested in this current, in drawing that, or in thinking about that, does the 7 cosine of 4t, when it's going positive, does it sort of help I get bigger? It encourages I. The other two are sort of discouraging I. They're sort of pushing against I because of the way that they are labeled polarity-wise, or how they've been inserted into our circuit. So if we keep track of voltage rises, which is, this is a voltage rise, let's just call that positive. So now, in terms of phasors, how does this one get converted? Now we want to convert this one. What does it look like? One, is it a voltage rise or is it a voltage drop? That's a drop, so we better put the minus sign in first so we don't forget that. And now it's a sine, S-I-N-E, and not a cosine. And we want all of our phasors to be relative to a cosine reference. The magnitude's not going to change, but what does need to be modified? This sine is at an angle of 0. What's the sine relative to the cosine? Does it lead or lag? And now just draw your curves and say, oh, the sine peaks later than the cosine by 90 degrees. So the sine expressed as a cosine is now minus 90 degrees. And finally, we have this source, and that, is it a rise or a drop? And now it's confusing because it looks the same labeling as the one on the left, but now it's on the other side of the mesh. So it's actually a drop relative to the rise that we're trying to be referencing with respect to. So this is now minus 2 at an angle of 0 degrees. So what's our total voltage source, phasor? Well, we can immediately add the 7 and the 2. Those are at the same angles. So we can now say, oh, we have 7 minus 2. And now how do we treat the minus 5? We're maybe trying, adding in polar form is not very convenient. It's easier to convert that to rectangular. And what does that look like? Now this is minus 5, and what's minus 90? Isn't that 1 over j? And now if we pull that j upstairs by multiplying by j over j, we end up with another minus sign. So now we have 5 plus j5 as our total voltage phasor. Or if you wanted to write that in terms of polar form, the hypotenuse is now a square root of 2 bigger than 5 either side, because it's a right triangle with acute angles of 45, and the angle up 5 over 5 is 45 degrees. That's now our source, and so now we could actually draw that. And we can now start sketching this in the frequency domain. What did we have? We had a resistor of 5. Does it matter where I put these? It was below before. Does it really matter? No, because they're in series. Now I need to convert the inductor to its frequency domain form. That was 2.5 henries. How do I convert that? That's j omega L. That's j times 4 times L. And then I have the capacitor, which in fact was 1 over j 4, and what was C? 50 millifarads, 0.05. And we were interested in that. I now have my impedance for the resistor is 5. My impedance for the inductor is J10. And the impedance for the capacitor is 1 over J. And that ends up being 0.2. Or if I pull the J upstairs and I divide by 0.2, my capacitor's impedance is minus J5. So that now the total impedance seen by this current is the combination of those three series impedances, and that's 5 plus J10 minus J5. Wow, that looks familiar. So it actually has the same complex number associated with it as the source's phasor did. This again is 5 square root of 2 at 45 degrees. And we can now say, oh, I can now compute the current through that circuit in the sinusoidal steady state analysis. That's V total as a phasor over Z total, which is a complex quantity. V phasor I can't promise the exam questions will be this easy in terms of computing, dividing one complex number by its equivalent value. That's pretty easy to compute. Now we know that the current phasor is in fact 1. 1 at 0 degrees. Can we say anything then about the phasor voltage of that capacitor? How do we find it? That's Ohm's law in the phasor domain. That's the impedance of the capacitor times the current I. Or what was the impedance of the capacitor? That was minus J5, and that's times the phasor current, which was 1. This is now, if I write that as a magnitude and an angle, what do I end up with? Five minus 90. Since minus J is at an angle of minus 90, we now have 5 at minus 90 degrees. Which says that we can now put this back into the time domain. Our sinusoidal steady state capacitor voltage is 5 cosine. Now what do I do? How was it shaking? 4. It was shaking. It has to shake exactly the way that we were exciting it before. And this is now minus 90 degrees. Or if somebody wanted to clean that up a little bit and maybe reduce the arguments complexity, we would say, oh, a cosine of something minus 90 is equivalent to a sine of that argument, omega t. This is now our sinusoidal steady state voltage across that capacitor. And we didn't have to do any calculus. Didn't have to solve any differential equations. Didn't have to play with sines and cosines except at the beginning and the end, when we were going from time domain to frequency domain, and then from frequency domain to time domain. Which basically says, oh, we can do all of our earlier chapter analysis as long as we keep track of impedances instead of resistors, and phasors instead of constant sources. Let's look at another example. Let's now find an equivalent impedance. And maybe, before I even say that, have we introduced... Did anybody take the tickets from the door, the admittance? Impedance and admittance, they are reciprocals. If we wanted to talk about admittance, then that's labeled as a Y, and it's the reciprocal of impedance. So Y, our admittance, is 1 over the impedance. This is the admittance. And in fact, we give that its own real and imaginary pieces. Don't ask me to remember these very often, but what is it? See, I even got it wrong. So the real part is a G. Good. And the imaginary part is a B. Well, good and bad. So we now have a good part and a bad part for our admittance, but now we have to get some new terminology. This G is called conductance, which is the opposite of resistance. That is okay. B is susceptance. And the units of admittance are Siemens. So now we have all these new terms to think about or to keep track of. And why? Well, if we had a Y admittance, W-Y-E, but the reason we might is if we had a bunch of things in parallel, we could just add admittances instead of having to combine them as reciprocals with impedances. All of that said is, let's say that we now have the following circuit. And we want to know what's the impedance looking in, let's say, to terminals A and B. And this capacitor is 5 millifarad. This resistor is 10 ohms. This capacitor is 2 millifarad. This is 5 ohms. And the inductor is 50 millihenries. Oh, and I left one out. This inductor is 100 millihenries. And now you're going, well, why'd you introduce admittance? This looks awful. Well, if it doesn't look too bad if you just combine these two and then you look at these in combination. Can you see the highlights? Now we're talking complex values or impedances and not just R's, L's, and C's. We could combine that 5 ohm resistor and the 50 millihenry in series. Those will add. And then these last 3 branches on the right are in parallel. And if we called this branch and said, oh, that has an admittance of 1, or let's label it as Y sub 1. This is Y sub 2, and this blue one is Y sub 3. Then we have the total of this, admittance-wise, is Y1 plus Y2 plus Y sub 3. That would be the advantage of using admittances. Then we could invert that and find its impedance of that sub-circuit, and then that's in series with the capacitor and inductor on the left. Is that clear, the strategy that we're trying to apply? First, let's find the admittances. Y. This is now, Y sub 1 is what value? If that's an admittance, that's the reciprocal of the impedance. What's the impedance of a 10 ohm resistor? The impedance of a resistor is the resistor. We're taking its reciprocal, so this is now Y sub 1. What's the impedance of this Y sub 2? That's 1 over J omega C. Oh, so we can't go anywhere, can we? We went into this restaurant and nobody told us what's on the side. We now have to be told how it is oscillating. Let's now assume that omega is 100 radians per second. So that now Z sub 2, getting too much color coding here, Z sub 2 was 1 over J omega C, 1 over J, this was 100, and what was the C? The C was 0.002. Or that's 1 over J 0.2, and we've already seen that before. That's minus J5. That's the impedance of that middle branch capacitor. We need to reciprocate that to get Y sub 2. And this is now Y sub 2, 1 over Z sub 2. And what's Y sub 3? Well, what's Z sub 3? Z sub 3 is now 5 plus J5. We reciprocate that, and that's Y sub 3. And there's our total admittance of those last 3 parallel branches on the right. We would then say, oh, we need to reciprocate that, and that will give us the impedance of the yellow box. And now we just add those 3 impedances, and that will be Z sub AB. What's this impedance here? That's 1 over J omega C. And this one is Z sub L is J omega L. This is J100 times 0.1, or that's now J10. And this one is minus J2. We can now put all of those together and end up with Z sub AB, the equivalent impedance looking into terminals AB. And then we could say, is it looking more inductive or looking more capacitive? In what way? We would just have to look at the sign of that reactance. We'll pick up with more analysis in the frequency domain tomorrow.